will now discuss the effect of external variables, like say if we vary pressure or temperature, what happens to the equilibrium constant. And that is connected to a principle which you already studied in your high school, which is known as La Satellite principle, which is named after the French scientist Henry Louis La Satellite. So what it says is that if you want to make a change in the system will try to counteract the effect by shifting the equilibrium towards the more favorable position. And that way the system will counteract the effect, or the external effect. Now, what we are going to discuss is the effect of pressure on the chemical equilibrium or equilibrium constant. Now, remember that equilibrium constant was connected to the reaction gives free energy, because it was minus RT ln K equilibrium. That's what we called as reaction free energy, the equilibrium constant. Now this equilibrium constant, which means is if it is connected to delta G0, what is delta G0? It is basically the standard reaction gives free energy. By standard we means actually the pressure was fixed at 1 bar. So already it is defined, or it is a well-defined quantity, that K equilibrium will be equal to, not equal to, it is connected to a change in Gibbs free energy that was carried out, that basically corresponds to 1 bar pressure, which means actually the pressure is well defined in the definition itself. So even if we change the pressure, there will be no change in K equilibrium. There should not be any change. However, RTL and Q can change, of course. The reaction quotient can change because that is not connected to pressure, but the equilibrium constant will not change. Now, when I say the equilibrium constant will not change, it doesn't mean the at equilibrium this amount of say A, B, and C, D, those numbers will not change. That does not no way mean that these things will not change. These may change, and we'll try to devise a formula how it changes. But the total equilibrium constant, which it is dependent on at equilibrium, that will not change. So that is the meaning of the response to the conditions, particularly the pressure. Now the question is, how will you increase the pressure of a mixture? Say in the mixture I have A, B, C, D, everything. And then one way to increase the pressure is that you insert some inert gas. Say we insert argon here. Now what will happen? The pressure will increase. However, this increase in pressure will cause nothing to the partial pressure of A, B, C, and D, because I can write the activities in terms of partial pressure by the divided by the standard state pressure, which is the 1 atmosphere pressure, and raised to the stoichiometry. Now, if you think in this way, so this is basically the expression for A, which I just used. Doesn't matter, it is for any constituent, we can write it. But the point here is that what is PA? PA is partial pressure. Now, what do we mean by partial pressure? It is the pressure of the gas if the same amount of the gas, of the said gas, would have filled the entire container. Like if I don't have B, C, and D, so the pressure of the A in the same container will be equal to its partial pressure. Now, which means actually it doesn't matter if I introduce argon or some other gas, which are we are by the way introducing inert gas to make sure that there is no reaction happens between it doesn't interfere with the ABCD system. So it should not react all by itself. If it reacts, then it's a different story. So we're just increasing the pressure. So if we introduce the argon gas here, the partial pressure of all these component doesn't change, because by definition, partial pressure is that amount of the constituent which basically, if the same amount actually fills the entire container, the pressure will be equal to its partial pressure. So by definition, that should not change if I introduce anything else. So the partial pressure remains constant, which means for each constituent partial pressure remains constant, so the K equilibrium also doesn't change. However, think about a slightly different situation. suppose we are introducing, say, suppose we, let's say, some kind of dissociation reaction. Say we have A going into, say, for example, 2B. So these kind of reactions are called dissociation reaction. Let me use a new page. So A is dissociating into, say, 2 molecules of B. That's what we are saying at dissociation. Now we had some kind of A, say we can denote it like this, and then we are breaking this bond. These are not actually necessarily atom, it may be a fragment, and this is also another fragment, and that we are dissociating to get 2 times of these fragments. That's the reaction. And a reverse reaction is known as association reaction, when these 2 fragments actually join together to give the parent molecule. Now suppose this is happening in equilibrium, and now what we have is that, and let us also assume that the degree of dissociation is alpha. So the alpha is the degree of dissociation, which you can actually connect it to your advancement of reaction. Degree of dissociation is alpha. Now suppose initially I had some mole fraction, let's say XA to begin with, and say XB to begin with, some mole fraction. So if the alpha is the dissociation, if when the reaction starts, and if alpha is the extent or the degree of dissociation, so the amount of XA that or amount or the mole fraction that will be present, it will be nothing but XA times 1 minus alpha. For B, it will be nothing but XB times 1 plus 2 alpha. Because if alpha is the degree of dissociation, it will be minus alpha for A, but that one molecule is giving rise to 2 molecules, so it will be plus 2 alpha for B. And we are just using a generalized notation, in the sense that initially it was XASB, and suppose we have at some time we have this much amount of degree of dissociation. So we can actually write the mole fraction in this way. So if you write it in, say, this fashion, XA, we can actually write the initial ones as a X0 or something. We can write it as XA0. Similarly for XB, we can write it as XB0, something like that. So XA will be nothing but, now look at it carefully. What will be XA? It will be nothing but 1 minus alpha times it will be the divided by the total thing. Now if you think in terms of the mole fraction, let us say that the total number of moles were, instead of writing it as XA0 and XB0, we can just write it as the total number of moles was X0. So then it will be easy for us to understand, because what I'm saying is that the mole fractions, total number of moles actually were X0. So now the mole fraction will be XA by XA0, whichever way you want to calculate. So XA by X0, that will be nothing but 1 minus alpha divided by the total number of moles, which is 1 minus alpha into 1 plus 2 alpha. So this is the total number of basically moles, which is proportional. Of course you have to multiply it by X0. So you can actually write it in this way, times X0 and times X0. So that will be nothing but the numerator, I'm getting 1 minus alpha, and in the denominator, let's see what we have. We have actually 1 minus alpha plus we have not 1 plus 2 alpha, it will be just 2 alpha. So we'll have 1 plus alpha here, and then the X0 cancels. So that's why I just took it as a total number of moles or something like that. So this will be the mole fraction of A. Similarly, the mole fraction of B that we are getting will be 2 alpha times X0, and denominator will be the same, 1 plus alpha into X0. So that will be nothing but 2 alpha by 1 plus alpha. Now what you can do is that you can just write the equilibrium constant in terms of partial pressures or the mole fractions, whatever you want to write. So let me write it as a first as a partial pressure. It is basically PB by P0, and let us write it down as this. Now it should be squared because actually we have in the stoichiometry 2, and divided by, why we are dividing, because it is -1, and PA by P0, but that raised to 1 only. So we can just now expand it. So it is nothing but the this is basically partial pressure, and we know that partial pressure is mole fraction into total pressure. So we can just write it. So the mole fraction is xp into total pressure, say is P, that's squared, and divided by similarly XA into PA, that's squared. Now look at the P0 terms. We have 1 over P0 square, 1 over P0, so there will be 1 extra P0. Sorry, this won't be squared, it's just raised to 1. Now what is XB into P? XB already we calculated. It is basically 2 alpha divided by 1 plus alpha, that squared, and XA, it is raised to 1 only, so it will be 1 minus alpha divided by 1 plus alpha. So just like P0, we'll have the total pressure. Sorry, this will be total pressure. It is P square here and it is P here. So there will be a P overall. So we'll have something like times P by P0. So that will always be there. So let us just expand it. So it is 2 alpha by 1 plus alpha squared. So it is 4 alpha squared divided by 1 plus alpha squared divided by 1 minus alpha divided by 1 plus alpha. So this 1 plus alpha will cancel with another 1 plus alpha, so giving rise to something like you can write it here. So it will be nothing but 4 alpha squared divided by we'll have 1 plus alpha remaining, and that will get multiplied with this 1 minus alpha. So I can write it as 1 minus alpha square times P by P0. So that is the overall equilibrium constant, or we can write it as Kp, or let us write it as K equilibrium constant. Now what we can do, we can actually solve it for alpha, just to look at what is the degree of dissociation and how it is connected to the pressure or the total pressure, how we can connect it. Now if we insert the inert gas, or in this case we can also use another way of increasing the pressure. You can think of our original discussion on this cylinder with a frictionless massless piston, and suppose we had these molecules around. So this is basically A, and suppose this is basically B. All of them are here, and then all of a sudden we are doing compression, and suppose we reduce the volume by, say, reduce the volume by, say, make the final volume as half of the initial volume. So the pressure will be just twice, because pressure is proportional to volume, and we are keeping the temperature also constant. Now what happens to alpha if we want to solve it? Just look at it carefully. I want to solve alpha. So the way we can solve it, it is 4 alpha squared divided by 1 minus alpha squared. So what we can do, we can just write 1 by K equilibrium, and that will be 1 by 1 minus alpha squared divided by 4 alpha squared. So it will be 1 by 4 alpha squared minus it will be 1 over 4 into, now I'll have P0 by P, and then I can take everything else on the other hand side and write it will be, basically I'm just multiplying it by the 1 over K equilibrium by this term, so, and adding 1/4 to it, and then let's see what happens. So we could have actually taken the 4 to be common, so it will be just -1, So what we'll have is 1 over alpha square will be nothing but, as we see here, it will be 4p by p0 into 1 over k equilibrium. So now we can see the degree of dissociation alpha will be the square root of the inverse of this quantity, which will be nothing but, if we write it in this way, 1 divided by, and it will be plus 1 also because there is a 1 here. So it will be 1 divided by 1 plus, I'll have 4 into p divided by p0 into k equilibrium. Now you can see that all these factors are basically constant, and now the alpha actually is, you can write it as something like 1 plus some constant into p. So if I increase the pressure, what will happen is that the system, it is showing that if I increase the pressure, alpha will decrease. Now why alpha is decreasing here? The reason is, if I go from left to right, so the pressure is increasing because every molecule of A is giving 2 molecules of B, and initially they are all in gas phase. So the total pressure is actually increasing. If I make this one net change where A is going to B, so then actually I twice the pressure. Now what I am doing is that I am externally applying the pressure and making it say 2. And if I make the pressure twice, then what will happen? The alpha will actually be reduced, and the reduction is happening in the other way, in the sense that now the B molecules will now do an association reaction and form more A molecules. So in the sense that in the equilibrium, the ratios should be constant because the K equilibrium is constant. It is already within a constant, so that is also constant. So if I increase the pressure, my alpha will change. So what it means is that, of course, pressure doesn't have any effect. However, we can actually control this ratio between the reactant and the products, particularly in the gas phase reaction. And that ratio, if I change, then I can actually control the ratio by changing the pressure. And this is happening because the equilibrium constant doesn't change. So the equilibrium constant doesn't change. However, the pressure of the individual things has to change in order to make that equilibrium constant same, which means the degree of dissociation will change. So this is a very simple explanation. You could have actually easily figured that out from this particular equation, that we have pressure of say B squared divided by pressure of A raised to 1 actually. So if I make the pressure of B double, in some sense, or say that here actually the example is slightly different. Here we are talking about the total pressure. The example we have given, it's not like if I double the pressure of B alone, then of course the equilibrium will shift towards left and by a proportionate amount. But what we are saying right now is the total pressure. If I change the total pressure of the system, then how it goes. So if I make this pressure as double, so of course it will not be reduce the alpha by half amount. It will reduce the alpha but to some extent, and that is happening because the equilibrium constant is independent of pressure. So it is constant, and since it is connected to the delta z0, which is actually independent of pressure by definition, because it is defined as the free energy change at a constant pressure, which is 1 bar. So it should not have any effect on pressure, because it is defined in that way. So we see that a nice demonstration how one can actually realize how LaSatelier principle is working, and how the degree of dissociation is changing, and how it is connected to the LaSatelier principle. Now we can talk about the second effect, which is the effect of temperature.